Okay, are you okay like this, or shall I use a mic?
Maybe we should try this.
Try this one. Sorry. Oh my God. Well,
Is the amplifier on?
okay. Right, so I'm Штыров, and I'm working at the Medical Research Council, Condition Brain Sciences here in Cambridge, where I'm a senior scientist. And for many years I've collaborated with the University of Helsinki as well, which is why you'll see lots of data from Finland today. God created Finnish language for psycholinguistic and neurolinguistic experiments. I'm fully convinced. And we heard about that from Jussi yesterday, and we'll see some examples today. Now, before we get into the topic, which is on attentional control versus automaticity in language perception, I need to ask you, we've got about, I think, this is a pretty lengthy lecture, depending on how many questions I get, and please don't hesitate to interrupt. So I think it might take a couple hours. The other two lectures are shorter, they're probably like 1 hour each. We've got this place until 4:30 in principle, but because of this being Saturday, the canteen, the cafe is closed. So would you prefer us to go on and finish with this and then have a lunchless session until maybe 3-ish, or shall we take a longer break between maybe 1 and 2? Or who would like to have a long break for lunch? Right, so I take it that we, okay, show a sister to the questions, right? All right, so let's get on with this. So the general question for today is, and it's just not for today, it's a question many scientists ask, is whether the human capacity to process language needs attentional resources, or whether it is automatic. In principle, the ease with which we use language, we can perceive the entire complexity. I'm going to talk about perception today, not about correction. The ease with which you can listen to me now while checking your email, perhaps, maybe you're writing something down, looking around, counting birds outside the window, and you can still hear me talking and understand what I'm saying. The ease with which we do all these things prompted suggestions that linguistic activity is a largely automatic cognitive function. Now, we can probably rephrase the question more precisely as to what extent this capacity to process language is automatic, or to what extent, to what level it needs attentional resources. Whether there can be some types or stages of language processes that need or do not need attention. If you look at theoretical background, there are all sorts of views on the issue. In sort of modular cognitive theories, there is a view of neurocognitive systems as encapsulated, that is operating independently from each other. Language, for example, being one of them, and they are thus not affected by other systems, such as attention system. In a different view, which is most prevalent in computational neuroscience, it's believed that everything interacts with everything. And Elman is one example, implying functional interactivity at all levels of processing. On the background of this come cognitive neurobiological theories of attention. You've heard some from Jyrki Tuomainen 2 days ago on Neil-Lavie theories. Similar ideas developed by John Duncan in Cambridge, actually before that, implying that there are limited resources for everything. So that your attentional resources are limited, and your functions, your cognitive systems, have to compete for those resources to get through this attentional filter. And language would be one of those, having to compete. Now, before we go into more experimental data, could you remind me what types of psycholinguistic information we have? I think we've got linguists here. Psycholinguists?
Of course. Both.
I know, you're the best student. I was one 2 days ago. I learned to keep my mouth shut. Right. I don't want to delay this. So, of course, you all know that we've got all these different levels or types of processing that are routinely discussed in linguistic, psycholinguistic literature. You can merge or merge these or sort of create new levels, but I think everybody agrees that we have a phonetic level, which is access to speech sounds. We have a lexical level, access to representations for words and morphemes. We have a level of morphology, which is structures of words, relationships between words, within words, within different morphemes of a word. We have syntax, dictating how words in a sentence fit together. We have semantics, describing the meaning of words, which is often not distinguished from lexical level, that often is. And finally, we have pragmatics, the highest level of language in context, in social context, in interactive context. And so far, automaticity has been suggested pretty much at all levels of these processes. From phonological analysis to lexical access to parsing morphology of individual words to semantic and syntactic processes, and finally all the way up to the level of a conversation, of a dialogue. How can we study such things? Of course, the most valuable tool to all of us is behavioral experimentation. And you've probably encountered some of this. Do ask me if you haven't. There are various behavioral well-established routines, such as priming experiments, lexical decision, masked priming, dictionating, which have been used for these experiments. Let's take some examples. At the level of phonology, there is a well-established, almost a seminal, pseudo-homophone effect. So you'll see a word like cream, spelled here. You see the cursor on the screen? I haven't got the point. So this is, of course, a pseudo-word, which is not a real word. So you put this in a lexical decision task. Do you know what lexical decision task is? Who doesn't know? Do I need to explain briefly? You have to say whether something is a word or not a word. So if you show something like cream, like this cream with double E, it takes longer for you to say that it's not a word than when you see something like jade, which is also a non-word, also different, just in a single letter from a real word. In mask priming experiments, a similar effect has been seen. So mask priming, ready to explain again? Mask priming, when you get a prime stimulus, which is shown so briefly and masked that you are not aware of that stimulus. And then another stimulus after that, which is called a probe, and then you see how the prime affects the probe perception. So if you show a prime, a pseudo-word prime, then it will ease perception of the real word later. More than this pseudo-word prime will ease the perception of a real word here. Both are different both are different in just one letter. Yet this has an effect and this doesn't. Why so? And the explanation is, and there were also similar effects in dictionary and in auditory modality and across modality. The explanation for this is that even though this is a visual task, you automatically access phonology, you automatically access the sound representation. You don't have to access that level in a task like this in principle. You only have to say yes, no. Yet you seem to activate phonological representation fully automatically. So that's automaticity in phonological access. Now let's look at single word representations at a lexical level. Here's another mask priming example. and different, and these are prime probe combinations. So you'll see that, and the higher the bar, the stronger the priming effect, so the more facilitation you get. And you'll see the biggest increase is a combination for something like lately late, which is semantically closely related, also informatically related, but it's stronger. It's a stronger priming than for something like boldly bold, which is similarly related on the surface, but it's actually not related in meaning, and that doesn't show an effect. So again, the prime is invisible. Subjects are not aware of seeing lately or boldly, and yet it affects the perception of the probe, which led these authors, published more on similar experiments from Cloud's group, to conclude that you automatically access lexical representations for these invisible prime words. Now, of course, the most famous demonstration of access to single word semantics is probably the Штыров effect. Again, you, Tomaino, made a little demonstration. Do you think we need to go through this briefly?
No.
He's saying no. I'm only asking because I know there could be people from different departments. I think I've been in simulation and biology department when we had to demonstrate that. So you know the effect. You can name these colors quite quickly. If I ask you to name the colors of these words, you can do it quickly. As soon as there is a mismatch between the color you have to name and the actual word, you tend to mess up. And this is basically an interference of irrelevant verbal information with non-verbal task. Your task is essentially non-verbal, non-linguistic. The task is just name the color. So reading the words is in fact counterproductive. It's against your instruction. It stops you from doing your task well, and yet you automatically do that. So the conclusion is, as Jyrki told us, is that you automatically process word meanings even when it's not required by the task. When it's even counterproductive. Now, this is visual. Now, in auditory modality, obviously you can't do the same things, but you can do other things. And for example, in diacritic listening experiments, when you have to attend to one ear while something else is presented to the other ear, properties of these unattended words will influence your task performance on attended words. This was shown by Штыров in 95, and I think I probably have to stop and say that Штырov died last year, killed by a truck in California, and it was a huge loss to cognitive neuroscience. It's a man who built his life in Israel, did a lot of excellent research, discovered a few fundamental things in cognitive neuroscience, and having lived in Israel where everybody sort of thinks it's a dangerous place to go, he always said, can't have a conference there because something happens and then nobody comes. And was just killed by cycling in California. Huge loss. Yeah.
I have a question.
Yeah.
Are there priming tasks or priming studies where they have had semantic prime, phonological prime, and then where they have combined semantic and phonological prime in one? So what is the effect?
Yes. Well, I think this is an example of what you're looking for. So you have lately late, which is both semantic and phonological. You have boldly bold, which is just phonological but not semantic, right? So in this case, and I think the amount of priming will change depending on whether it's masked or not. So here you have facilitation. I think I might be wrong. If it's unmasked prime, you actually have inhibition for boldly bold, like you have here for yellow yell. That they would share their phonology and their surface orthography, but actually are not related at all. So now we get we've mentioned behavioral evidence for phonology. We mentioned behavioral evidence for lexical access, for semantics of single words, and even for syntax. There is evidence of automaticity. And a lot of this work is done in Edinburgh by Gert and Pickering. In Edinburgh and in Glasgow. Simon Gert, of course, in Glasgow. And they showed things like syntactic priming. So you automatically copy syntactic constructs. If I now start talking to you in passive voice rather than active voice, you'll find yourself responding to me in passive voice without realizing that. So humans seem to automatically, without conscious understanding of that, copy whole syntactic constructs. And here I'm citing something that allegedly was said by Garrett, cited by Ford, that what you have to remember about parsing here, meaning syntactic parsing, it's a reflex. And this was suggested up to the level of dialogue, where Garrett Pickering suggested a whole theory of automatic alignment of dialogue participants. So you automatically, without consciously doing this, align your mode of communication with your partner in the dialogue. So coming back to our questions, whether some types of language processes can be automatic, I think we've seen from behavioral studies that there is quite a lot of evidence for that. From psycholinguistics, from behavior. Is there any neuroscience support for it? Is there any neuroscientific evidence? Now we have to keep in mind a few things about doing neuroscientific experiments. You had an interesting presentation yesterday by UCN on planning your experiments, and I'm going to chip in and offer a few advices as well. Typically you ask your subjects to attend to words, to sentences in your experiments, to the language that you give them. Often the tasks are actually quite linguistic in nature. You have to do you ask them to do a lexical decision task to judge whether something is a word or not. You ask them to do a grammaticality judgment. You ask them whether syntactically a structure is correct or not. So it's actually quite a demanding task, which requires attention on the input and active processing of the input. How, under such experimental conditions, can you really say, establish automaticity or attentional control in a linguistic function? And when you do this, you register brain responses. What will be registered? Will you register brain responses to language, or to task side effects, or to attention variation? We know that attention responses modulate brain brain responses, including structures quite close to language areas, frontal areas, parietal, to a temporoparietal junction, where one of the main language areas would be close to attention network. So it will be very easy to confuse the effects of the two. And when you do things like I've just described, such as grammaticality judgment or lexical decision, when subjects are shown pseudo-words, which they have to judge, it's a very unusual task. You don't really encounter that in your daily life. Could that demand more attention? So when the sentence is incorrect, could it be that you pay even more attention than usual? Therefore, your attention level is modulated actually with the task, completely contaminating your data. So you need to control for such things, and it may not be a trivial thing. So actually, for delineating automaticity and attentional control, you want to control and quantify effects of attention itself. Perhaps for confirming automaticity as such, you want to remove attention altogether. And I'll show you a bunch of experiments that did that. How can this be done, and which neurophysiological tools would we use? Now, again, before going into the tools, I think we need to remind ourselves that language is a uniquely human property, meaning that you are pretty restricted in terms of tools you can do. You can't just stick electrodes in most cases, or take it apart and see what breaks, like any neurophysiologists do. It's also a remarkably fast function, so it changes with time. Information keeps coming all the time, changing, and you need to track of that. It's very complex, and it occupies more than one modality. It's at least auditory and visual. We discussed that we can use behavioral tools, which have been extremely valuable and still are. But if we want to talk about brain, we want to talk about neural processes, then of course they are not a direct reflection. They are reflecting your neural processing by proxy. In the last 20 years, we saw a rise in neuroimaging, including tools with superior spatial resolution, such as functional magnetic resonance imaging, PET, more recently near-infrared spectroscopy, which have good qualities in terms of determining where activity in the brain is in space, but don't really have time resolution. They can't tell when something happens. And with something like language, when you can output words at a speed of 5 a second, fMRI resolution at 6 seconds is not satisfactory. And as I'm going to advocate, you've heard yesterday talking about event-rate potentials. For language, for real language, probably the best tool is real-time brain neurophysiology, electrophysiology, magnetoencephalography, electroencephalography, something that may not have best spatial resolution, although that's increasing with new tools that we're getting, but has excellent time resolution. We heard it talk on ERPs yesterday by Ari, so I hope I don't have to repeat that message. I'll still ask you what we know about language ERP components. What are the main components you would name? And for 100, good. Could I get another?
Elan and P600.
P600, well done. Yeah. Well, I think, cool, you'll hear lots of that. I think you've nailed down the main components. There is actually quite a bunch, but Elan for 100 and P600 are probably the most famous ones. And here is a super complicated diagram from a very good and influential review by Angelo Federici, director of Max Planck Institute in Leipzig, who linked different ERP components here on the right to different linguistic processes here and different brain structures over here. We can zoom into this and see how nicely she aligned things from primary acoustic analysis to word form identification to integration of morphological information, finally to reanalysis and repair at all these different stages, starting from N100 and going on to Elan and N400 and P6, so it's like a sequential process. We'll question that later, but that's an established view, which we need to acknowledge. Now, what could we do, coming back to our question? So we have these ERP components, which we can register if subjects have to do something, some linguistic activity. How can we control effects of attention? Let's look, I'm going to load you with studies from our group. You'll be crying for help in the end, probably, but before we do that, let's see how this has done this. So let's again look at this example from Leipzig. And a couple of papers from Anja Hane, who tried to control effects of attention. Obviously, the obvious thing you would think of is change experimental task instructions. And what they did in this paper with Angelo Federici is to record event-rate potentials to spoken sentences which had or had no syntactic phrase structure violations and semantic violations. So sometimes grammar rules were broken, sometimes also the meaning was just wrong. And they changed the task. They either asked the subjects to judge the overall correctness. Just tell us, is this an okay sentence? Or in another task, they asked them to judge semantic coherence and ignore syntactic errors explicitly. So if you hear a grammatical error, just ignore that. Tell us whether it's semantically, whether the meaning is okay. And they found an interesting thing. So when with sentences that contained only semantic violations, and the subjects were asked to judge correctness, they did find an N400, a very famous. It's always the first response that people mention when I ask the question. Very famous response. They find it with semantic violation when you're asked to judge correctness. Now, when there was a syntactic violation, and again, the task is to judge overall correctness, you get Elan and P600, so you get established syntactic responses. The first is Elan, which happens at 100 odd milliseconds, early left anterior negativity, and P6 later. And what happened when they combined, it's the most interesting thing, when they combined semantic and syntactic violations in one sentence, and they had their two tasks. in a task where, remind you, there was task number 2 was to judge semantic coherence explicitly, and task number 1 was to judge just overall correctness. So in a task when they ask the subjects to ignore syntax and concentrate on semantics, they got all major components in this number 2. In the task when they still ask the subjects to judge correctness without explicitly mentioning either syntax or semantics, they only got syntactic responses. They only got ELAN and P6. They did not get N400. Sorry. So this led them to a conclusion that initial syntactic parsing, especially ELAN task, ELAN response, is independent of task requirements. It occurred, the syntactic responses occurred even when subjects were asked to ignore syntax. And yet, N400 only occurred in those situations when subjects were explicitly asked to judge semantics. So the conclusion is that it reflects control processes. It does not reflect any automatic obligatory processing of flexibility. This is very good. We could say that there is still a little bit of a problem perhaps with this study, is that the subjects are still having to pay attention. In both tasks, they are paying active attention to stimuli. And I mentioned at the beginning that we kind of have difficulties quantifying the levels of attention. So they did another study, even though that was done earlier, I put it later, because I think it logically fits here. And here, rather than changing explicitly task instructions, they decided to do it implicitly. They changed experimental settings. Again, they had sentences with and without syntactic violations. And here I have some examples. I'm not good at German. Why does it keep changing when I move the cursor? You'll see the right sentences with obvious syntactic structure violations. And what they did, they gave different ratios of these sentences. In one condition, incorrect sentences made up 20%, and in the other condition, they made up 80%. And they said if you get 80% of syntactic errors, you're going to ignore them. So that's how we will define attention, by changing settings. And that's what they found. They found early left anterior negativity, this early response, 120 milliseconds often, with focus here in left anterior areas of the brain. They found it in both 80 and 20%, 80 and 20% conditions. It's here. What happens with P600? P600 is usually visible in the back of the head here, this positivity posteriorly. It's almost disappeared. Well, it wasn't significant in the 80% condition. So the conclusion is, and a very nice conclusion is, the first pass, the first pass stage of syntactic processing, the very early stage of parsing syntactic structure, which we assume is reflected by ELAN, is automatic. Whatever you do with the task is there. And remember, it was there even when the subject didn't have to pay attention to syntax. The second pass is on the strategic, on the attentional control. Very nice. Now we can criticize this again. We can say there is still a task to attend to sentences. They still have to pay attention. We don't know how much the level fluctuates with correctness, for example. And there is this implication that high probability of errors leads to low attention. Is that really true? Can you say if I start talking to you with many errors, mispronouncing things and making syntactic mistakes, does that actually mean that you'll be paying less attention? Or perhaps if I switch to strong Russian accent and completely forget English grammar, you'll have to pay actually more attention to make sense of what I'm saying. So is that really a good assumption? There could potentially be priming effects. So if you get lots of sentences of the same kind, they might prime each other, thus reducing responses, which we know priming does. So the question is, could we do better? Could we modulate attention more directly than that? Now here's another paper which did exactly that, and that comes from Helsinki, from Ralander and colleagues, who published this in 2009, I think, in the Journal of Neuroscience, who gave subjects combinations of primes and targets, which were either related, so two words that are closely related, I don't know, gem, eat, or words that are unrelated, gem, run, I'm just making this up, and they gave their subjects three tasks. To ignore spoken words and watch a film, just passive distraction, or to judge whether words end in the same letter. This is how it's described in the paper. These are spoken words. To judge whether they end in the same letter. So it's a kind of phonological task, which they argue does not promote meaning processing. You just need to analyze phonology. And finally, they ask the subjects to judge whether the two words are related in meaning. Do a semantic readiness task. Now, what they found, these responses look quite different, but what they concluded, the N400 is a difference between the thick and the thin line. And what they concluded is the N400 in both active tasks, so in the letter task and in the word task, it's an equally strong response. That's the conclusion of the paper. They also say that there is a small but significant N400 effect in the passive task. So there is a small difference here in the And the conclusion is that there is semantic processing outside the focus of attention. So even though you're paying attention to the film, you're still getting some of 100 to those unrelated items. And there is still modulation of semantics by controlled processing. And finally, from the fact that the letter task shows N400, so here you don't have to actually process word meaning, you only have to process the letters. There is still a response, and the conclusion is that you still automatically process semantics when you pay attention. So there is some semantic processing all the time, basically. There is modulation by task, but there is also automaticity. I think that is for everybody. Now, as I'm trying to follow Eustace's advice to be critical to everything, so I'm going to question this study as well. The letter judgment, is that really a good task? You can really say, when you're given a task, process letters in spoken words, that this is a shallow processing of phonology. Actually, letters are written, not spoken, right? So a better question would be, do they end in the same sound rather than end in the same letter? Although Finnish, pretty much like Russian, more than Russian, is very transparent in terms of letter to sound. Still, it might prompt you to analyze the word, imagine it, print it, and then analyze it, which might lead to actually deeper processing than you want. One general comment I'd like to make about any priming study is that priming studies talk more about the relationship between the prime and the target, the prime and the probe, rather than process the word per se. So it's not the same thing. We're not really looking at responses to a word itself, but looking at the relationship between the two in a pair. And one thing that I'd like to note to you, yes, they looked at the N400 size, which is, they judged as the same here, and smaller here, and they never interpreted huge differences in the overall responses. So you'll see, even though the difference might be similar, the overall shape of responses hugely changed with the task. Between this, and that, it's quite different. And finally, they completely ignored anything that happened before the N400. You'll see the tiny differences all over the place here in the first peaks, and here as well. Now I'm going to show you the data that many of you will have seen. One of the studies we did using mismatch linkability design. There'll be some old stuff and some new stuff at the end if you make it to the end. I think you all know that what this response is. Do I have to describe to anyone? It's a normal task where you have an occasional replacement of a standard stimulus by a random median stimulus. The key things is that to produce this early cognitive response called the mismatch linkability, you don't need any attention at all. It's produced during sleep in subjects who are in coma, as long as they will wake up later and will not die. So it is automatic in that sense, and therefore is a good candidate to test it. It reflects responses to individual items. So you can focus on single items and therefore scrutinize responses without smearing that may be caused by averaging across many different types of words. It does allow for unique designs because it's a different response to a change. So you can incorporate the same change to different contexts, for example, to lexical context, to phonological context, or to syntactic context. It was originally suggested to replace to reflect short-term memory processes and change detection, and later to reflect also long-term memory traces, originally by now in 1997, for just single phonemes, and later we developed this into a whole business of lexical and syntactic distinguishabilities. So here's one example where subjects are exposed to words and pseudo-words which with standard and deviant stimuli being played to them when they are not doing any stimulus-related task. They're actually being distracted by watching video, and all these conditions, words, verbs, nouns, and pseudo-words, are acoustically near identical. They have the same contrasts, you just get a change in a single letter, and a standard becomes a deviant, and it's the same letter in all conditions. And what you find is this is an energy device, and these are maps seen from left and right. And you find a left lateralized response. This is field topography, which is larger in size, and left lateral for verbs and nouns, but not for pseudo-words. So even though you're not paying attention, your brain responds differently to these items. We can find it in left and right temporal cortices, about 150 milliseconds in this study. And we can also try to find its analog with fMRI, which has slightly better, somewhat better spatial resolution than MEG or EEG. And again, you will find temporal, this time it's superior temporal with middle temporal activation, which is significant for words and bigger on the left, but when you look at pseudo-words, it's just not there. It's certainly not at the same significance threshold. There is, of course, some activation, but that does not pass significance. So what we seem to have is an early, as we know from electrophysiology, enhancement of automatic responses to unattended words in comparison with matched pseudo-words, which we explained repeatedly by activation of long-term memory traces for words, which happens in superior temporal areas before 200 milliseconds and has by now been replicated in different languages. We started with Finnish, English, that was done in German, by now Spanish, Chinese, Thai, so all sorts of languages, as long as physical properties are still there controlled. More recently, we looked at finer grained properties of this response. So this seems to reflect the activation of memory trace, which happens even when you're not paying attention. That's the explanation. More recently, we looked at this modulating the frequency of words. Why is that important? So the explanation for strong activation is that you actually have a representation which becomes active. For pseudo-word, you don't have a representation. There is nothing. There is nothing to activate when you don't pay attention, especially. And the idea behind the memory trace is that it needs to be created, which is created by, or through learning procedure. When you learn words as a child, you create new representations, they become formed, and then they become active every time you hear a word. Now, then there could be stronger representations, such as for words that you use more often, and weaker representations for words that you use less frequently. And we tested this in a study using a similar design, but with words of different lexical frequencies. And this is a study by Lily Kimber, who's here, did a perfect job with this, who compared a set of Finnish words. This is not exactly any specificity, but it's a similar idea of presenting a small set of words in a passive presentation without subjects paying any attention. And here, Lily and us we had a set of Finnish words, quite similar acoustically, which were played again and again to our subjects who didn't pay any attention to them, and we had pseudo words, which differed from words just in single letter, but obviously didn't have any subjects didn't know anything about them. And what we found here is a very strong correlation between the size of this frontal negativity, early negativity, which was in this case about 120 milliseconds, and the word frequency. So it was increasing linearly with frequency increase. This is mean subject data, and you'll see that this is individual subject data. You'll see that it's actually true for most single subjects. And these are not here. This is correlation quotient plotted on the head surface. You'll see the correlation is very strong here between 100 and 120 milliseconds frontally, and maybe more to the left. And these are significance levels. Again, you see the same thing. When you put the same data for pseudo words into the same analysis, these are acoustically matched pseudo words, you just don't get anything similar at all. When we look at sources of these effects, we find that all these words, low and high frequency, they activate temporal areas, even both hemispheres. But for high frequency words, you have a selective increase here in anterior temporal and inferior frontal parts. And it looks like there is also increase in prefrontal. So these are part of core language areas, and including parts that are related to articulation. So it's a network of areas going into the left hemisphere. So we have a passive auditory response, which is increased for words as opposed to pseudo words, which is enhanced for high frequency as opposed to low frequency words. We replicated this in Russian with a different design here in Sibizro with Professor Alexandrov's group. And the explanation still holds. So there is an activation of a long-term memory trace, which takes place automatically, seems to be an index of lexical access, happens automatically and without any focused attention on the stimulus. So we'd like to believe that this is a reflection of automaticity in early access to words in the brain. Okay, we have that. We can see not only automaticity, we can also see where and when in the brain things happen. Note the difference with plain psycholinguistic studies, which I don't want to question, but in addition to getting some sort of behavioral outputs, you might as well get values of when things happen in the brain and approximately where in the brain that happens. We can even see that this response can indicate the strength of memory traces. The stronger the memory trace, the better the connections, the bigger the response becomes in passive presentation. Can it tell us about the meaning of words? Now, I'm going to switch to something you may be well aware of. It's the idea of embodied language, which is closely linked to the idea of mirror neurons. And the idea is that in addition to your primary language areas, you actually use your category-specific ones to encode specific meaning. For example, for words related to visual objects such as sun or tree, your visual areas will be involved that are responsible for perceiving color and brightness. And an iconic example which was suggested by Friedman Putfermuller, with whom I was privileged to work for many years in Cambridge, is that of action words. And the beauty of this idea is that motor areas are topically organized. Your leg is controlled by motor cortex on the top of your head, and your face is controlled. Your face muscles are controlled by different bit of the motor cortex. So you can see these things are quite distant on the brain surface. Therefore, the suggestion is that why don't we play subjects words that are related to different movements, to movements related to kicking, for example, to waving with your hands, or to eating with your mouth, and see whether these areas indeed play a role in activation. There are many studies using fMRI and TMS, but some of the strongest evidence comes from these from these electrophysiological studies where we presented the subjects words like kick and pick passively without them even paying attention, and what we found is a very strong difference in brain responses to these quite similar words. Typically you would see this, I just showed you maps of activation with this frontal activity. Now suddenly when you play a word like kick, again, the subjects are distracted from this, you see a very different pattern. It's a more posterior focal response. You play them a word like pick, and it's also a different pattern. It's central and it's stretched out to both sides. We do source analysis with this, and we find a dorsal source compatible with the leg representation area, which becomes active, in this case, at 170 milliseconds after the word was presented. We did the same in the MEG, in the MEG, with better source resolution, and we could see how the activation progresses from core language areas here for, I know it's not eat in Finnish really, it's more like gobble up, but it's the best match acoustically for the word kick. So for this face and hand related word, the activation just gradually crawls up. For the leg word kick, it just jumps up to this dorsal location. And now you can even make like even a small film out of this and see, again, you can see even more with neurophysiology than I just showed you. You can see how things change gradually. They develop with time. You see sort of persistent temporal activation, and these category-specific activations appear and disappear in different times at different places. So we seem to see aspects of referential semantics reflected in spatial temporal patterns of activations. Clearly seen with action words. What about other kinds of words? Can we do that? So this is a study which I'm probably giving up on because the postdoc who ran it changed 3 jobs since, for which I wrote a few reference letters. Every time he said I'm almost finished with a paper when he wanted the letter, and the paper is still not there. But anyway, it's a great guy actually, Campus Study, who's now at Trisha Kuhl's lab in University of Washington State, who ran this study with, again, using words related to different actions, look, lick, and lock, and also he included abstract words. Words that are acoustically similar, but don't mean anything specific. Abstract words like clack and lock. And what he found, a lot of auditory activation, which you can see in temporal lobes, but the differences came from the frontal areas where we can't see that this is a source estimation using medium norm. And this activation is obviously driven by auditory activity. The auditory cortex produces a lot of it. And to find any category specificity, we need to zoom into small areas and analyze that almost blindly. And that's what he did. And what he found is that yes, you still have category-specific activity, about 100 to 200 milliseconds, such as for the word look, you have frontal eye fields activation. And for the word lock, you have more of a hand area increase. I'm struggling with the cursor here. And now for more abstract words, he found prefrontal, even inferior prefrontal areas becoming active. So what he finds here is differential activation in motor, premotor, and prefrontal areas very early on to unattended words, and that activation depends on the meaning of words. Motor regions were activated again for action words, and inferior frontal, prefrontal areas for abstract words. And of course, we know that prefrontal areas get more input from different parts, they play more associative role. And it only makes sense that they will be involved in abstract word encoding. And they need more features to integrate. So it seems like we can find lexical and semantic information reflected in brain responses that appear to come from distributed sources, distributed across the brain, that include your basic language areas in temporal lobe, in frontal lobe, but also those outside your traditional Broca areas. The information seems to be available to them very quickly. 100 to 200 milliseconds, they're done, and they don't even need you to pay attention to activate that representation. Now, I'm going to skip this. It's interesting, but it's on how you can learn things learn words without paying attention to them. But we will skip that, unless you really want me, and talk a little bit about another study done in Finnish using contextual semantics. So I mentioned a study by Randa and colleagues, and this is a similar idea, although in more simplistic design, where subjects were played with minimal combinations, two-word combinations that either matched or mismatched in their meaning. An example I made, jam kick and jam eat, and you can do the same with football kick and football eat. And again, we instructed subjects completely and scrutinized. The idea, of course, in Finnish is that these words are quite close acoustically. So you'll see these prime words, jam and football, illo and pallo, and the critical stimuli, again, hotki and potki are quite close acoustically, so which means you can align your stimuli quite closely, and you can zoom onto a specific area where a word can be recognized, which gives you an advantage over those studies where you use multiple different words, although it has a disadvantage of having only few items. We'll get to that later. What we found is that contextual mismatch elicited an increased response in temporal areas. So the same words presented unattended and presented in a mismatching context produced bigger activation in over-temporal lobes in the left hemisphere. That's the topography on the bottom. Surprisingly, this was extremely early. This was an average of 116 milliseconds, and you will see how small this difference is. So this is grayed out difference, which I just mentioned smearing responses with uncontrolled stimuli. So if you had large groups of stimuli, it would probably disappear. This would probably be removed. This was maximal sort of between 1 and 140 milliseconds, and more recently we found similar time course even for pragmatic processing, so for language perceived in context, as occurring at the same time. Now I'll briefly run through the same design done in syntax, so combinations that either match or mismatch, and I'll just show you the responses again, at this time about 200 milliseconds, suggesting that ungrammatical context elicits in unattended situations larger temporal responses in Finnish-speaking subjects. Now, in this syntactic study where the subjects weren't paying attention to these errors, we did not find frontal source, which is often found for ELAN, and that could probably be explained by the method. So MEG is less sensitive to some sources than EG. We do find frontal source for this activity when we run EEG. We didn't find any effects on the latency, and more interestingly, we did not find any late responses at all when subjects didn't pay attention. And that brings us back to the Friederici and Honey studies I started with, who concluded using very different manipulation. You'll remember they manipulated the probability of incorrect sentences, and they found that ELAN response, early left anterior negativity, was not affected by that. It was present always. We find the same with this syntactic mismatch behavior response. Even when the subjects do not pay attention, you still get this early activation, which is probably the same as ELAN really, but we don't get anything like P600, which seems to reflect late attention control processes. This is an example of the curves. You see another difference, and you don't see anything late. Now I think we can skip this. So you will remember the picture I showed in the beginning from Angelo Friederici, with everything happening nicely in sequence. And here, if I remind you of the times, we saw for lexical, semantic, phonological, and syntactic processes, I always talk to you about 120 milliseconds. So it seems like most of these things, not only do they happen automatically without you paying attention, all of these early things happen at the same time for different kinds of processes. So this seems to replicate more of a parallel access to different kinds of linguistic information. Again, yet another sort of outcome you can get from neurophysiology, as opposed to perhaps some other methods. Now, how are we doing with time? Actually, doing pretty good. I think I'm going faster than I hoped. You want 5 minutes? 5 minutes break, or shall we rock on? Yeah, let's go. I think everybody's interested in our early lunch or beer without thinking of tomorrow's lectures. So let's go. So I've spoken to you about these linguistic responses in the oddball designs, which I list when subjects are not paying attention. We politely call them out of attention focus. We're not really, it's difficult to say attention independent. Perhaps because we don't actively distract. Subjects are distracted from auditory stimuli. They don't do any task. They don't judge the stimuli in any way. They usually watch a video, and often they have to answer questions about what they saw in there. And then if we see that somebody wasn't really watching, we just kick them out, because we know they could have been listening to us, to our words instead. So we've taken this presence of word or syntax or semantic specific ERPs or even fields, ERFs, as signs of automaticity. And this was discussed in the literature, point of view reviews by Nat, and also point of view by our group. But this can be easily criticized. Is this distraction really effective? This is a passive distraction, which is, you watch a video, whereas some sounds are being played. Is this really attention free? And Bob Kaline from Cambridge, he once made a comment in his kick statement in 2004, can you sneak a little listen now and then? And that certainly is a big question mark, and therefore I'd like to say that we need more systematic modulation of attention to establish that in fact early linguistic processes are as attention independent as we wanted to believe based on these data. So here is yet another finish line. I have a instruction for this.
About this automaticity, how much do you even think that human behavior is like what can you call automatic, like attention free? Because we are all the time we are conscious, we are attentive, so it could be division of attention to certain stimuli, and we are always surrounded by things that we are constantly attentive in some respect. Anyways.
Yes, that's a very good comment. So I think you're probably right that we had this discussion with Jürgen Thormann the other day, who suggested that you just constantly switch your attention, so you never fully withdraw it from something, which can be true. You can divide your attention into modalities. It's more difficult to divide your attention within modality. So it's, again, as in those gorilla experiments which you've seen, you can fully ignore a stimulus even though you are staring at a screen. And in Jürgen's demonstration of the auditory version of the same, you can be fully ignorant of an auditory phenomenon occurring when you have to pay attention to something else. Your system is quite good at filtering things out. You can still argue that there is residual attention, and maybe this is what we have in the form of this response. You have some residual processing going on, which is necessary to react to ecologically valid stimuli. So if you are a human in prehistorical Africa, just acquiring your first language skills in evolution, and you're doing your primitive pottery at home, and a cheetah comes to the village or to the settlement, and somebody cries a cheetah, and you have to run, and you're so involved with your pottery that you don't hear that. I think you're dead, right? So there needs to be a mechanism. So there needs to be a stage of gating where this first response might lead to attention reorientation, or it might stay out of the focus of attention. Whether we call that low level of attention or we call that pre-attentive processing, as some like to, is I think maybe a terminology process. So certainly the system registers the change. Yes?
How about in sleep? Because it's argued that we are conscious while we sleep, and also this cheetah while you're sleeping is very important to pick up.
Well, I think it would be difficult to argue that your attention to external sources in sleep is as good as when you're not, because when you're asleep, you're likely to be eaten in that case, or in recent days, burgled into a house.
But there has been studies about sleep that, like sleeping in groups, the ones that are sleeping on the outer, like there are 3 people, and then the ones that are sleeping in the
And that's a different kind of sleep. They
are
don't
like-
sleep. They
they
don't
are-
sleep the same sleep.
Yeah, their sleep is more shallow. So has it been studied that actually could you get some response in sleep for linguistic stimuli if they even get it for coma patients?
Well, you get them for coma patients for non-linguistic stimuli. So you get a change response in coma patients who will recover. You get a response to a normal design, but not the group in Marseille, a French group, who did the study with coma patients. They claimed that they tried it with patients' own names, and they did not succeed. But then we've seen many things not succeed, and then when we take them and try to do them properly, they do. So I think it's one of the things which has to be done. I'm not aware of any studies. You're welcome to try, maybe. Right, so that's another Finnish study, where this time we went back to basics and decided to tell our subjects explicitly, pay attention or do not pay attention. And subjects listen to a group of words and pseudo-words in Finnish, and that what happens with response to words and pseudo-words when subjects are not paying attention to the stimuli. You see the same thing I showed you before. The early response is stronger for words. This time the peak is at 120 milliseconds again, when subjects do not pay attention. What happens with word responses between the 2 blocks? Compare the unattended and attended conditions. You will see that this early response, which we saw, shows this lexical effect. It doesn't seem to change for meaningful words at all in the first phase. It does change later. The early difference, the one with an arrow here, the early peak is the same. It doesn't change significantly. Later, this time 130 milliseconds, and then another peak at 370 milliseconds, you have a difference caused by attention. Early on, nothing, 0. Now, when you look at pseudo-words, actually it's a different picture. They actually are changed in the same way by attention in these later two peaks. But also early on, the pseudo-words actually grow in size, and also in the early time interval. So they exhibit different behavior in attend and non-attend conditions. We can find these effects of attention if we do the maths, so we can compare. We can compute the difference between attend and non-attend conditions. And obviously for words, you see the differences wishy-washy. There is pretty much nothing early on, which then develops into left anterior positivity and later more spread out negativity. That these later things are pretty much the same for pseudo words, and which also show a very early effect that is strongly left anterior. And if we try to analyze their sources using distributed source analysis on the brain surface, we end up with inferior frontal areas for attention regulation effect, which later becomes a lot more spread out, so across different areas. In this case, inferior frontal, anterior temporal, and a lot of parietal, pretty comparable with what we know about attentional networks. So it seems like the early word elicit response was not affected by attention manipulation. which isn't true for pseudo words. So this experiment could suggest that early lexical access, by lexical access we mean activation of representation for word, seems to be indeed automatic. It does not change with attention, but only the early stage. So it could be that these memory circuits, which we believe are strongly interconnected groups of neurons, many thousands of them, are robust enough to become fully ignited even when attentional resources are low, but by giving them more attention you don't get any more activation at the same level. So you get full activation, the memory traces are high and robust, and they become active. At later times you still get attentional effects, which seem to be modulated by left peripheral, but also by parietal areas. This was Fini Shiji. We did this experiment in MAG in English, which was published by Max Garignani, and he found a very similar effect. Again, here the two red lines are word responses in attend and ignore conditions. You'll see they're quite close and they're not significantly different. But the two blue lines are pseudo-word responses in attend and ignore conditions, and you'll see that pseudo-words don't just increase in size, but they actually overtake words in this case. So it's a major difference. Why this is a bigger increase here in English is probably because of the task. The task was attention task was a lot more rigid in this case. So it seems like we have stable word activations. A sign of lexical access, as I keep talking to you about. But now pseudo-word activations are modulated by attention. We need some explanation for this. So obviously we keep talking about mathematic lexical access, automaticity in language access. So what's happening with pseudo-words? They don't seem to be fully automatic. They are influenced by attention demands. We need an explanation for that. Explanation for words is easy. You have good, solid connections, they become active. Now, pseudo-words seem to need resources to be processed. So when you're not paying attention and you hear a meaningless item, you are not likely to give it any notice. It's irrelevant. It's ecologically irrelevant stimulus, which is not necessary to analyze. When you do pay attention, then you have some space to analyze that, and you might try to reanalyze or repair it or do something with it. And one explanation for these activation is the one that I came up with based on lexical labor activations. This is closely linked to the cohort model of speech perception. Do I have to explain a little bit the cohort model? So I think I should say one word. The idea is, in spoken language, you activate every possible candidate. So when I say starts by saying crow, your brain accesses crop, cream, cry, crude. All these words are pre-activated to an extent. When I get on and it becomes a crop, then cream is already out, cry is out, crop is still there, crony is still there. When I get to croc, I think you are left with the crocus and one other word, which becomes fully accessed at the stage I reach crocod. You don't even need the full thing to know what crocod is going to be. That's known as a word recognition point, defined by William Morton Wilson, which is a whole separate topic in itself. But the idea is, when you get these incomplete items, you activate a whole cohort, which is why it's called cohort model. You activate a whole cohort of words. And that could be what underlies the pseudo-word effect. So when you don't have resources, you activate nothing. You perhaps process some basic auditory features of this stimuli, but you don't activate lexical representations. Or maybe you activate some of those neighbors, but really to a minimal level. But now, when you do get to pay attention, when you have enough resources to analyze those words, then all these possible completions could be partially activated. They never reach full activation because they are not complete. yet they are not ruled out because there is no single candidate. When you finally get to crocodile, then that alone will suppress all other candidates. All other activations will die. In case of pseudo-words, you never get to crocodile. You just have these partial candidates, and you don't know which one of them I may have meant when I said crocodile. So you have to access maybe a few. Did he mean a pile of crocs or something else? So that's the idea for why pseudo-words behave quite differently, why they modulate, why they are modulated by attention. And that's an experiment that actually needs, that's something that needs to be tested experimentally by including words of different, with a different number of lexical neighbors. And that's what we're doing right now in Cambridge. So, now I've described to you these couple of experiments where we modulated attention, where the subjects either ignored the stimuli or they had to do something, they had to listen actively. And we saw this increase. You can still ask me the same question. So what have you done? Did you remove attention completely? You talked to us about automaticity. But your subject is still either paying attention or they're just passively distracted. Indeed, they might still, in the passive condition, we still can't establish whether they are listening a little bit now and then or not. So what we need is an opposite approach, which is a more rigid distraction which will take attention more fully away. And that's something that has not been fully done in auditory modality with lexical access, but that's something that was done with syntax. Syntax is something that is repeatedly discussed as an automatic process. And this experiment was done with two levels of distraction. So in one case, subjects are getting this stimuli. They get these little phrases, we come, and sometimes they get we comes, an obvious syntactic error. Now the trick here is they only get it in the right ear. What they get in the left ear are these tones, which go beep, and you can see that they're much louder. But sometimes, at the same time, when the syntactic error occurs here, so that's where your S is, you get a little change, which is quite small and difficult to detect. And that's their task. They have to detect that. And that comes to your left ear. So that's distraction within modality, which is a lot more difficult. You can't share your attentional resources across modalities. You can pay attention to an auditory and a visual stream. We're actually trained to do that. We always listen and watch. But within modality, it's a lot more tricky. So that's within modality. And that's a very heavy task. And there's another one where again, they listen passively. What we find this is a complicated graph, but you don't have to know too much about that. The key thing is you have the red versus blue is grammaticality effect. So the red is bigger than blue, which means you register grammatical error, or your brain doesn't at least. But what you see is the difference. What is important here is the difference between dashed lines and solid lines, and that's attentional manipulation. And you'll see that both blue and red ones go together up until approximately here. And up until here, they don't have any significant difference between themselves. And later on, they start to diverge. So after 140 milliseconds, there are huge effects of task, but not before. And that's syntax. Now, these studies, I showed you two lexical studies, EG and MEG, of Finnish and English, on single words, and one EG study with English sentences. So they use different languages. They use different contrast. It was lexical versus grammatical contrast. They used different techniques, EG and MEG, and MEG was done in two different labs. And the attentional manipulation was quite different. We had more rigid attention to stimuli as opposed to passive distraction, or we had distraction within modality from syntactic errors. So rather different things. Yet we seem to find remarkably similar time course. What we find in both cases is the earlier stages of event-rate responses did not change with attentional demands. It seems that both lexical and syntactic ERPs were immune to attentional effects in the earlier stage. And that's the same stage where they show specificity. They show specificity to syntactic or to lexical properties of stimuli. At a later stage, you get accumulation of attention effects. Again, we can go back to the studies of Hahn and Federici I mentioned in the beginning, and Leipzig group did a few other studies along the same lines, including a very good investigation by Anna Husting, who worked with us and moved to Leipzig, who, using different approaches, use the same thing again and again. And the earliest, although Leipzig only work on syntax, they don't believe in early lexical access. That the earliest stages are there, whatever you do to them. You pay attention, you don't pay attention, you do different things. And more recently I saw a mask priming study, which book from is from, but the same things happen again and again. Early effects seem to be immune to attentional manipulations. There was a model, a computational model by Max Berliani, who's working in Cambridge and is now in the process of moving to Plymouth. Computational neuroscientist who produced a model built on a few layers of language cortices, sort of taking the main areas in the temporal and the inferior frontal areas and their connections, and making this into a computational model, and then training this model with words, something that the model knows, and testing it with those words and those items that the model never learned before, and manipulated attention. Attention was manipulated, so what he did here is building in feedback inhibition. So there are these nodes which provide inhibition. The more you activate here a certain layer of cortex, the more this inhibition node suppresses it. So he has this feedback inhibition, which in his view is a model of attention. The more you inhibit, the less attention. So absence of attention means you suppressed certain processes. And he found this remarkable thing. So with the level of feedback, this is just arbitrary units, so with a lower level of inhibition, he gets this increased response for pseudo words, for the items the model never learned before. And when he cranks up the feedback, there is more suppression in the system, pseudo words drop tremendously. But look at the red curve. This is the items the model learned, and the model activates for them whatever the feedback is. So that's a beautiful demonstration of the same effect in computational terms, and a model of how it might actually take place in the brain. So automaticity seems to apply to different types of linguistic information. It seems at the same time be limited to the very first stages of linguistic processes. Going back to the question we asked in the beginning, whether there are certain types or stages that are automatic or attention control. It seems like many types, if not all, I can't show you anything about pragmatics at this stage. Many types are automatic, but not all stages are. Only early stages appear to be immune to attentional demands. And later steps are affected by attentional location. These later steps, which probably reflect a more in-depth secondary processing, maybe reanalysis, they are dependent on the amount of resources you have for language. Otherwise, you could, do something else now, write your essay for next week, and listen to my talk at the same time and perfectly remember everything. That's not going to happen. So it seems that full processing of spoken language is not possible without allocating attentional resources to it. And the allocation itself, coming back to Lily's question, might be triggered by early automatic stages, per se. So, I'd like to make a few side remarks and then continue the talk a little more. You still okay? We're probably going through most of the talk. Shall we go on? Yeah, all right. So one thing I'd like to touch upon is the difference between the responses I showed. I showed a lot of early responses, mismatch integrity, but not only. Similar responses when you just play words or sentences to subjects when they are passively listening to them. So we get a lot of early responses, but others don't. And for 100 is the most well-known response. You can acquire it easily. And why that difference occurs? Why is there? Why do we get kicked by referees all the time when we submit these early data? Although less and less these days. And my first answer is that you should just look for it. And this is a quotation from Gospel of Matthew.
How long did you search for this when you found where it is?
Yeah. So, I mean, that's how actually Mr. was found. It was found by Christian Martin in somebody else's paper as a belief that the original authors never looked at. So it's the same here. Look at a typical, it's one of the headquarters of N400. People in Leiden and Funberg and lots of nice studies. Huge N400 for anomalous context. And they ignore the early effects altogether. They're small. Early effects are always small in size and they disappear quickly. In the first 200 milliseconds, you have a brain response that goes down and then up and down and up again, and it disappears. It's a lot easier to analyze something like this that lasts for 200, 300, 400 milliseconds. So one thing is you probably should just look for it. Now, another explanation, of course, is that many of those typical 100 tasks, they use attention. They do things that I described at the beginning, lexical decision, semantic judgments, whereas we try to distract people. Could this be that attention is the one that's responsible for this difference? And indeed, look at what we saw. I showed you this EEG data. When the subjects don't pay attention, we see the early difference. As soon as the subjects start paying attention to words and pseudo-words, this disappears. And as I showed you with Maxer and Young's EEG data, it might even go the other way, so the words might produce larger duration. So attention could be another reason for these differences. There is also one other thing, and that's the confounds of the paradigm that I described. We repeat stimuli many times. We just choose a few words which are perfectly matched, but very few. And we drill our subjects with them for an hour. You would hate to be a subject. But we show nice movies and play in the end. So the small number of items is a confound as well. It's not an ecological stimulation. So I'm going to show you a study where we try to avoid that and still test where the early effects stand. The difference to previous studies was that now this MEG work done first authored by Lucy McGregor, published earlier last year. What we did is record the MEG to more than 100 of English words and pseudo-words. Not a single one of them was repeated more than once. But we did our best to match them psycholinguistically and acoustically. They were all monosyllabic words and pseudo-words. And we made sure, I described you the word repetition point in here, we made sure that they could not be recognized up until the last sound in the word. So they had many neighbors up until they saw the words like kick, pick, lake, take, dip. They have many neighbors, but at the last phoneme you know what that is. Or it's a pseudo word, which means nothing. So she recorded energy to these items, and that's what she found. That's global activation to this difference. By the way, these are spectrograms, average spectrograms of words and pseudo words. You see how closely matched they are. And she found lexical effects, again, when the subjects weren't paying any attention. She found them in the same time range where we saw them before, about 150 milliseconds. She also found effects in the later time range where a standard N400 design would see them. And quite surprisingly, not something we fully expected, she found them a lot earlier, peaking at 65 milliseconds, starting from 50 and actually even earlier. There was a lexical difference occurring between 50 and 90 milliseconds in this case. So this being energy, we obtained single subjects brain images and did proper source analysis on traditional language areas in temporal lobe and inferior frontal lobe. And what we found is the very early lexicality effect, the one at 65 milliseconds. or if you come from the word recognition point, even as 40 milliseconds, as occurring here in the left temporal areas. You see more activation here at this early time for unattended words than pseudo words here on the right. You can see how it moves later, so you then get more activation. This is 120 milliseconds. You already have inferior central activity, a little bit of inferior frontal too, although not significant at this time. And finally, reaching more into frontal areas as soon as 160, and even more at 400 milliseconds. That's the picture of the same thing, and it's a more complicated. These differences are bilateral. Also, right hemispheric temporal cortex plays a role. So what we seem to see is a very fast response, not just the 120 millisecond response, which we replicate, we also see a very fast response. If you think of this, it's actually not surprising. We're used to hear about lexicosemantic ERPs at 350, 400 milliseconds. But if you actually look at neurophysiology and you calculate the times it takes for the auditory signal to travel from your outer ear to auditory areas, it's only 10, 20 milliseconds, which we know from neurophysiology. If you look at how long it takes from temporal areas to Broca area, for example, it's only another 15, 20 milliseconds. And even across to the other side of the brain, across the corpus callosum, it's another 10 to 20 milliseconds. So you can actually pass the signal from your outer ear to anywhere in the brain within 60 milliseconds, which is pretty cool if you think of this. But if you go back to the cheetah example that I made, that's probably the time that would allow you to react. If you had to wait for nearly half a second to react to your tribesman message about the danger, then you'd probably be dead. We are animals that developed in evolution to react to events in our environment, and we want to react as soon as possible to survive. Therefore, our brain provides for information to be transferred very, very quickly. And it seems, indeed, to react to information in this early time frame. It even reacts to meaningful words within 60 milliseconds. So we have lexical access which is ultra rapid. We have responses distinguished between words and pseudo words in these early times. As I said, 50 to 90 milliseconds after the recognition, after acoustic event allows recognition. From actual word recognition point, it's even less. And we see that this early response is not the same that I showed you before. It precedes the later stage. We can still see these later stages separately. So it's a distinct stage, which probably nobody saw before, because nobody controlled the stimulus to the same extent. And we in our little experiments probably killed this effect with repetition, or maybe something else. So there's a new distinct stage, which corresponds well to the theoretical conduction delays that we know from neurophysiology.
Can I ask?
Yes?
How much repetition do you think that kills the effect?
You never know, but there is a well-known P50 repetition effect where you present 2 clicks, and the P50 response, the one at 50 milliseconds, is much smaller to the second click than to the first click. So that's what I think, and if you repeat 100 times, then I think you're sure to kill that. Now, interestingly, we found more recently, and that's not published, we found a P50 lexicality effect in older subjects, which were tested for a completely different reason, but we know that with aging, the P50 suppression effect disappears. Whether it's because the brain changes, or maybe some other things, but the suppression effect disappears, and you can see a more expressed P50 response. So it's one example where it's not a reduction with aging, but an increase, a more expressed P50 response in older subjects. And suddenly we could see this lexicality effect in those people. So that's another support for the idea that it was probably just the repetition that kills. Another thing is that typical filters for P50 response are not the typical filters used in neurolinguistics. So you would usually filter 1 to 30 hertz, and in P50 research they would filter 30 to 100. So it's a completely, I can't say the lexical response is P50, but it's at least in the same time range. So it seems like we have this very early response supported by temporal and late inferior frontal areas, which again occurs automatically when subjects don't pay attention and does not seem to be an artifact of multiple repetition. Happens for more ecologically valid designs. Now, what happens with higher? So this is again for lexical access. We just described single words, presented many times. We talked in the very beginning of the study by Helsinki Group under et al. With priming design and how different tasks modulated M400, but M400 was still there. And I made a remark that there seemed to be early differences which were not analysed, and we tried to do a similar thing ourselves. Now, being encouraged by this first finding by Mr. McGregor published in Nature Communications, we tried to do the same thing with context. So we took a group of well-controlled, monosyllabic words and looked in Edinburgh semantic database for words that are related to them as opposed to words that are not. So these are examples: Swan Lake as opposed to Swan Late, and you can have a counterbalance. You can think of it as a counterbalance design such as early late and early lake, and we've got more than 100 combinations like this, not a single repetition, and recorded MEG responses to these. And this is very new data, still not fully analysed to be in preparation. But the subjects had to do, again, 3 tasks. They either passively listened, they watched a film, we did a little bit more rigidly, and before we asked them questions in the end to make sure they really watch it, and they pay attention to small details, not large details, not who playing, it's not a question of who is playing the main character, Bruce Willis or John Travolta. It's a question about what colour was the handbag of the lady when she left the car to go to the restaurant. So a few of those, we really make sure they pay attention to a distracted task. Then we ask them to do a phonological task, which is a gap detection. We insert a gap, so rather than hearing late, they hear late, which is easier to detect for Finnish speakers, but it is a non-existent contrast in English. So it's a hard phonological task. But it's not focusing the attention on the meaning of these combinations. And we also ask them to judge explicitly how related these two things are. So it's a semantic task. Now, what we found, preliminary data again, we found again an early difference. These are pretty lousy looking curves, but in all 3 tasks, the early difference at 50 to 80 milliseconds produced a significantly bigger response for related combinations. So it seems to have to do again with activation of representations for these items, maybe pre-activated by the context in this case. These are sources for these effects, and they are again left temporal for this early relatedness effect. Now, at this early time range, it was not affected by the task. So the effect statistically was the same for all 3 tasks. Later, you have the reverse effect. You have an increased response for semantically unrelated combinations. And later again, you have a more like M400 response. And both of these are affected by task. So what we find again, using a very different design, is a super early activation that is sensitive to semantic variation, this time to context integration, but is not affected by the task demands. And later on, you get task demands effects. So we seem to have this ultra-rapid automaticity that precedes a cascade, at least, the main peaks 2 more, probably even more, processes of attention-modulated nature. And you see how later it's a whole mosaic of different things going on across the brain. I'm not going to focus on that. Yeah.
About this, that this was MEG, so do you think that you will get more if you combine MEG and EG about the sources?
Yeah, actually, this is combined MEG and EG sources. you get more. And you get more. You get when you combine MEG and EEG, you get frontal sources a lot better than you do without. You see nice and clean inferior frontal sources here, for example. Right. Okay. Now, for the final stretch of this talk, I spoke exclusively of auditory modality. And I started by saying many things. One of them was language is multimodal. So what happens in the visual modality? We spoke about mask priming designs, how a stimulus that you mask still affects your perception of a stimulus that you don't mask. But what about the kind of experiments that we did in auditory modality? So removing attention, presenting stimuli in oddball designs. And this is an example of a recent study which was done here. It's an academic thesis of Galina Garayeva, it's in the biological faculty, who tried to implement the same design, oddball design that we developed for lexical contrasts in auditory modality to visual task. And what was done here, the subjects had to concentrate in an EEG experiment, the subjects had to concentrate on a dual task in the center of the screen. They got these concentric circles, and they had to respond to, say, a combination of a green inside, red outside. And these combinations changed all the time, and you had to pay attention to both features, the colors and the location. And this is a so-called dual task, which requires a lot more attention and makes you very focused. And that's the kind of thing you do with Gorilla when you likely to ignore everything else. So in this case, green outside, red inside would not be your correct answer. So this thing was present there all the time by changing colors. At the same time as this was changing colors, words were flashed for just 100 milliseconds on screen periphery. So here and here. So these were either words or pseudo words, and 2.5 degrees from the center, so it's already piriforming area. It is by definition not in the center of your visual attention. And I just finished the manuscript. What we find when we look at these responses to words and pseudo-words presented, unattended words and pseudo-words presented in visual modality, we find a remarkably similar thing that we saw in the auditory one. So these are responses to, these are global field powers, so a combined response across all electrodes, all subjects. You find a big increase for meaningful words, the red curve here, maximum 114 to be exact milliseconds, and pseudo-word response much decreased. We also had non-words, so hash marks, ampersand signs, or the set, or something that's non-phonological in nature. That's equally decreased. So we seem to be getting exactly the same signature of early automatic access to lexicality, to lexical familiarity in visual modality, as we do have in the auditory one, implying some similarity in mechanism of attention control between the two modalities. We did a similar experiment with MAC in England and English stimuli, and this time again, this is not an oddball design anymore. These are more than 100 of different words, never repeated again. And the subjects have to pay attention to these combinations of circles, symmetric circles, while words are flashed again on the periphery. But now it's not an oddball design, and a different language, and a different method. It's a MAG. And we find MAG being, 306 channels of MAG being a lot better than 28 channels of EEG. We find a little bit more data here. So what we find, I truly hate this thing. The mouse, I'm sorry. So what we find is the first difference between words and pseudo words occurs here at 90 milliseconds for English. You see, if you plot the topography, it's above left temporal areas. In a little bit later, so this is the peak here in the temporal areas. Just a little bit later, at 150 areas, it peaks in inferior frontal parts of the brain. So it moves here, and you can see this is a curve from inferior frontal sensor. That's where it happens then. Even later, after 200 milliseconds, it takes a different polarity. It becomes a higher response for pseudo words, something we know well from earlier 400 studies. We can try to plot sources of these effects, and we find familiar places in the temporal lobe. And now these are visually presented words, so we also get something occipital, possibly inferior temporal as well. These data are very much in progress, but I hope we submit them this year at least. So we seem to have an enhanced response for unattended words now in English, as well as in Russian, starting from very early on, in this case from 90 milliseconds, which seems to confirm the idea that we have automatic neural processing of linguistic information, which is true for, or universal for both auditory and visual modality. And it's probably, again, a first-pass processing that precedes later attentional dependent stages. So I think I'm now in a position to conclude. I hope I don't have any more slides. I may not remember. I apologize in advance if it's not the last one. So we can record very early traces in the brain for specific linguistic processes if we carefully construct our stimuli and carefully look at the results. We can see that all sorts of linguistic processes respond in response to spoken, and as I showed in the end, also to visually presented language, can be seen to start very early. They commence from 15 milliseconds and go on after that. These early processes, such as those that reflect memory trace activation for words, for lexical entries, are robust. They can be activated automatically, whether or not we pay attention to them. Early automaticity seems to exist for a whole variety of language processes, at least for lexical, syntactic, and semantic, but later it does give way to a cascade of attentional control processes. I think I've sent these papers through Alexander, and I can just say that there is a review that I wrote a couple of years back, and there are a few original papers that I could give you if you want to read. And I'd like to thank a number of people in Cambridge, in Helsinki, and also now in Berlin, Moscow, and St. Petersburg. And thank you for attention. Right, shall we take a small break? And we'll go on. We have a lunch break, right? We have two short